Welcome to the third lecture on graph theory. So, in this lecture we will talk about Hamiltonian graph and bipartite graphs. So, before I start I just want to recall the theorem that we proved in second lecture, that if G is a simple graph with n vertices, and if the degree of every vertex is greater than or equal to n by 2, then G is Hamiltonian. So, in this proof, this is a proof by contradiction. We considered a maximal counter example to this theorem. That means, G is a graph, is a counter example having n vertices, and it satisfies all the conditions that n is the degree of every vertex is greater than equal to n by 2, but it is not Hamiltonian. And this is a maximal counter example in the sense that if you add one more edge to this graph, the graph will become Hamiltonian. So, probably this is a little difficult part. Let u and v be two non-adjacent vertices of G, then there is a Hamiltonian path joining u and v. This is because, see, u and v are non-adjacent, and if you add this edge, u v in the graph, then the graph will become Hamiltonian. That means there will be a Hamiltonian cycle, and if you remove the edge u v from the graph, there will be a Hamiltonian path or spanning path connecting u and v. So, this is I think I wanted to mention once more this one, and this theorem is due to Dirac. Okay. So, next we move to one more example. According to Dirac's theorem, the following graph contains a Hamiltonian cycle. Find it. Let me draw the graph. It is slightly complicated graph. A B, C D, E F, G H. So, there are 8 vertices, and A is adjacent to G, F, C and D. B is adjacent to H, G, D and E. C is adjacent to A, adjacent to H, F and E, and D is adjacent to F, G and A and B, E is adjacent to B, C, G, H, G and H, and F is adjacent to H, A, C, D, and G is taken care already, H is taken care. So, this is a graph. I just I am giving this example to illustrate Dirac's theorem. So, this graph has 8 vertices, and you can see that the degree of every vertex here is equal to 4. So, 4 is greater than or equal to n by 2, which is 8 by 2 equal to 4. So, this satisfies the graph, satisfies the condition of Dirac's theorem, that every vertex has degree greater than or equal to n by 2. So, the graph is a Hamiltonian graph. You find the Hamiltonian graph, you find the Hamiltonian cycle in G. You spend some time to find the Hamiltonian cycle of this graph. Let me just give the answer here. This is one Hamiltonian cycle, A, C, F, H, B, E, G, D, A. You can check that this is a Hamiltonian cycle, and it is a Hamiltonian cycle because it includes all the vertices A, B, C, D, E, F, G and H, and A again because it is a cycle. So, this is what the Hamiltonian cycle for the graph given here. Next, we talk about another theorem. This is due to Bondy. Let G be a simple graph on n vertices. Suppose U and V are two vertices in the graph such that U and V are not adjacent, they are not an edge in the graph, and degree of U plus degree of V is greater than equal to n. So, in this case G is Hamiltonian if and only if G plus UV is Hamiltonian. Okay, by the meaning of G plus UV means this UV was not an edge in the graph G. Now, you add this edge UV in the graph G, that is the meaning of G plus UV. So, now in G plus UV, UV is an edge. Let me prove this one. G is Hamiltonian, and I have to prove that G plus it is given that G is Hamiltonian, then I have to prove that G plus uv is also Hamiltonian. This is obvious because if you add one more edge in the graph, in a Hamiltonian graph, the graph will remain Hamiltonian. So, there is nothing to prove here. So, G is Hamiltonian, then obviously G plus uv is Hamiltonian. Okay. Now, the other part that it is given that G plus uv is Hamiltonian. We need to prove that G is Hamiltonian. Okay, so this part is not obvious. It is, you are given that G plus uv is Hamiltonian, and then G is also Hamiltonian. So, you are removing a specific edge from the graph. Then after removing an edge, the graph might not remain Hamiltonian. So, you need to prove this is a non-trivial part. So, we will prove this part now. So, we need to prove that G is Hamiltonian. So, this proof is again by contradiction. Suppose G is not Hamiltonian. Suppose G is not Hamiltonian. Okay. Then there is a Hamiltonian path or spanning path or spanning path in G joining U and V. This is obvious because G plus uv is Hamiltonian. Now, you are removing one edge uv from that graph G plus uv, then there will be a spanning path joining u and v in the graph G. So, the same very similar argument. So, u and v, and there is a spanning path joining them. So, V1, V2, exactly the same proof, Vk minus 1, Vk Vn minus 2. So, this is the spanning path joining U and V, and then again we do the same thing. We have seen the proof of this one, that if U is adjacent to Vk, then V can't be adjacent to, this is not possible, V can't be adjacent to Vk minus 1. If U is adjacent to Vk, then V can't be cannot be adjacent to V k minus 1. Okay. We sort of agree with this one because of because otherwise there will be a Hamiltonian cycle here. Assuming that this is correct, let the degree of u be equal to k. We do not know what is the value of k. So, V is then is not adjacent to at least k of the n minus 1 vertices. Because if u is adjacent to something, V can't be adjacent to its neighbor. So, V is not adjacent to at least k of these vertices, because u is adjacent to k vertices. So, V can't be adjacent to its k neighbors. Thus, the degree of V is less than equal to n minus 1 minus k, and what we get is that degree of u plus degree of V is less than equal to n minus 1 minus k plus k, which is equal to n minus 1. So, this is basically less than equal to n minus 1, which is a contradiction. Okay. So, G is Hamiltonian. Okay. So, this was a proof by contradiction. We assumed that G is not Hamiltonian, then we came to a contradiction that degree of u plus degree of V less than equal to n minus 1. So, finally, we proved that then this assumption is not correct, G is actually Hamiltonian. So, next we talk about a concept called closure of a graph. The closure CG of a graph of order n is obtained from G by recursively joining pair of non-adjacent vertices whose degree sum is at least n until no such pair exists. Well, so the closure of a graph is you start with the graph and look at the non-adjacent vertices and you compute their degree sum. If the degree sum is greater than or equal to n, where n is the number of vertices of the graph, you add an edge between these two non-adjacent vertices. Okay, so, let me give an example to illustrate how to compute closure of a graph. Example. Okay. This is a nice example maybe. This graph is having 6 vertices, and these are the edges of this graph. So, this is the graph G given, and the number of vertices is equal to 6. Now, I compute the closure of this graph, that is C G. Well, so the closure of this graph is obtained as follows. This is the same graph I am drawing again. These are the edges of the original graph G. Now, I look at these two vertices. These two vertices are non-adjacent, and the degree of this vertex is 2, the degree of this vertex is 2. So, the degree sum is 4. So, the degree sum is not greater than or equal to 6. So, I do not do anything here at this moment. Now, you see that these two vertices are for these two vertices the degree sum is equal to 6. So, I add an edge between these two vertices. Now, I look at these two vertices, for example, these two vertices now. So, here the degree sum, this is degree 2, this is degree 4. So, the degree sum is equal to 6. So, I can I add an edge between these two. Now, this has degree 2 and this has degree 4. So, I can add an edge between these two. What about these two vertices? This is of degree 3, this is of degree 3 now. So, I can add an edge between them. This is of degree 4, this is of degree 3. So, the degree sum is 7, I can add an edge here. This is of degree 3, this is of degree 4. So, degree sum is 7 greater than equal to 6. So, I can add an edge. So, now this graph has become a complete graph, I believe. So, this is a complete graph with 6 vertices. So, this is the closure, this is the closure of this graph. Now, if I take this graph for example, so this graph is also having 6 vertices, the graph G, which is a cycle of length 6 C6. Now, you can see that there are many non-adjacent vertices here, but the degree sum is 4, which is not greater than equal to 6 for any non-adjacent vertices. So, you can't basically add any edge here, the closure of this graph is the graph itself. Okay. So, we have explained what is a closure of a graph. Now, it has some consequence. So, theorem: a graph is Hamiltonian if and only if its closure, if and only its closure is Hamiltonian. The proof is very simple, because you know when we add a new edge, this is coming from the previous theorem that G is Hamiltonian if and only if G plus UV is Hamiltonian, where we know that U and V are two non-adjacent vertices in G, and they satisfy the condition that degree of U plus degree of V is greater than equal to n, where n is the number of vertices in G, and this is the condition for adding a new edge UV in closure. So, this is the proof of this theorem comes from here, that G is Hamiltonian if and only if G plus UV is Hamiltonian. Okay. Now, to establish a graph is Hamiltonian, it is sufficient if we show that its closure is complete. If the closure of a graph is complete, graph, then the closure is Hamiltonian. As the complete graph is always Hamiltonian, so G is Hamiltonian. Okay. So, the concept of closure is somewhat important, because to prove that a graph is Hamiltonian or not, one way to find check whether the graph is Hamiltonian or not is to find whether the graph contains a Hamiltonian cycle or not. The other way of proving that is that you find the closure of the graph. If you see that the closure of the graph is a complete graph, then the closure is Hamiltonian, and then the graph is also Hamiltonian. And you must have noted, or it is easy to note, that complete graph is a Hamiltonian graph. Thank you very much for your attention.